So the Root-Locus method, what do we do in here? Basically, once again, we will try to figure out performance of the system, stability of the system, and all those things from the location of the roots. But in this case, the poles or the roots of the denominator or the characteristic equation, it will have an unknown variable, which will be gain of the controller. And as we change the gain of the controller, we will get different poles and different zeros of your system. And if we start accumulating, well, we're going to get different poles rather, not zeros, but if we start accumulating all those poles and connect all of them together as we are changing the value of the gain of the controller, then the collection of all those poles is called Root-Locus. How does it help us? As you will see, it will help us trying to figure out what exact value of the controller gain can produce a specific poles or poles on the y-axis or poles on the left-hand plane or poles on the right-hand plane. So from the Root-Locus, we can easily figure out what specific value of k is going to produce any of the specific pole for the system, for the characteristic equation of the system. There are 7 steps to sketch the Root-Locus. And you guys are very fortunate that I don't require you guys to sketch it by hand. I used to ask a student, but then it was pretty difficult for some of the students. So, and then I realized, there is really no point of, because again, with the advancement in the the plotting techniques and MATLAB and control system toolbox and stuff, there is really no need to sketch it with hand. When it was devised in like 1948, of course there were computers, but very early computers, and there was really no proper method to kind of put together the sketch of all the roots, all the poles of the characteristic equation, and then combine them together to create a Root-Locus of a control system. So at that time, some of the control engineer named by Evans, I don't know what was the first name, the last name was Evans, he put together these 7 steps to sketch the Root-Locus. And these steps, we're going to discuss those, but as I said, you're not going to be required to sketch it by hand. We're going to be using MATLAB for sketching purpose. And actually, your second project is going to be from Root-Locus, that you will have to create a Root-Locus of a characteristic equation which is given by the user. Now, there is also a function in MATLAB that can do the same, but I will ask you to do it in a little different way so you can understand actually what is the purpose of Root-Locus. So what is Root-Locus? What do we do? Observe this unity feedback control system. You have the controller gain. So this is your GC and this is your GS. So this is your controller and this is your process. So controller gain, which is K, when it will be changed, then it is going to change how the process is going to be controlled based on the error it is receiving. So once you are changing the error, once you're receiving the error, sorry, not changing the error, once you're receiving the error, based on the likeliness between RS and YS, you can change the controller gain in order to control the process such that YS start becoming closer and closer to RS, as we've been discussed so many times. The transfer function is simply going to be GCS GS over 1 plus GCS GS. All of us know that. So GC is K. So KGS over 1 plus KGS is the transfer function of this closed loop control system. Now this is where the poles of the transfer function are going to come from. This is where the zeros are going to come from. So to calculate the roots of the characteristic equation, so this is my characteristic equation, Q of S, as it is seen over here. To calculate roots of the characteristic equation, QS is equal to 1 plus KGS. We will equate it to 0 because that's how you calculate roots of any polynomial. So 1 plus KGS equals 0 to calculate the roots, to calculate the poles of the transfer function. Now remember, S-plane is a complex plane. So KGS we can write as -1 because 1 plus KGS is 0. So KGS is -1. Or we can write it down as -1 plus J0 just to represent that this is KGS is in the complex plane. Now, since we have a complex number, we have the magnitude, we have the phase. So the magnitude is going to be what? Magnitude of KGS is simply 1, which is the magnitude of this. And the phase of KGS, remember, it's a negative number. That means it lies on the negative real axis anywhere. That is 180 degrees. So anytime you have a negative real number in the complex plane, that number which lies on the negative real axis, it has the phase of 180 degrees. So the phase of KGS is 180, or of course it can be repeated plus K 360 degrees. So every time it will rotate 360 degrees, it's going to be on the same negative x-axis. So the phase of the KGS can be either 180 degrees, 180 plus 360, 540 degrees, 180 plus 720 degrees. So all of those phases will correspond to the phase of KGS because 1 plus KGS is 0, KGS is -1. So keep this in your mind because this is going to help you find out the value of K for any specific root of the characteristic equation. And of course, keep this in mind as well, but this is important. Okay, so our QS, the denominator of the quadratic equation of the transfer function is 1 plus KGS. So QS, I'm writing 1 plus FS. FS is basically your KGS. And Fs can be given by K times, which is the, of course, controller gain. S plus Z1, S plus Z2, S plus Z3, all of them, S plus Zm divided by S plus P1. So these are the poles, these are the zeros of the transfer function of your process. And these are the poles of the transfer function of the process. So GS can be written as S plus Z1, S plus Z2, all divided by S plus P1. So you have M zeros for GS and N poles for GS. That means if you calculate the magnitude of Fs, which is equal to 1, because the magnitude of KGS, if we equate this to 0, that is -1. So the magnitude of KGS is 1, and KGS is f of s. Magnitude of f of s is equal to 1. So magnitude of f of s is simply going to be k, which is magnitude itself. It's a real number. It's not a complex number. Times the magnitude of s plus z1 at any specific value of s, magnitude of s plus z2, and at that value of s, and so on and so forth. So any value of s in the s plane, you can put that value, and you can calculate the magnitude of f of s, and that magnitude should be equal to 1. And likewise, to calculate the phase of f of s, Remember, phase of f of s, since f of s is a function of s, and s is a complex number, and it's a fraction. So how do you calculate the phase of a complex fraction? How do you calculate phase of a complex fraction? Phase of A is, guys, complex number, guys, complex number. Please review your complex number. I put those lectures as well that I created just to help the students out. But the complex number is a constant struggle, and they're not difficult. Just review them. They're not difficult. How you calculate phase of this fraction, which is written in the complex form? Who's gonna tell me?
Can't you convert it to polar and subtract the two angles?
Okay, so what is going to be? If I want to write down phase of A is what?
It would be inverse tangent of B over A minus inverse tangent of the D over C.
That is correct. Arctan of B over A, that's the phase of the numerator, and then the phase of the denominator is arctangent of C or D over C. And when you are calculating the phase from a fraction, then you subtract phase of the denominator from phase of the numerator. So arctan of D over C. So once again, guys, you guys know complex number. If you're struggling, review them. It's not a new thing. You've done complex numbers before in circuit analysis, before that in math class. So something that you should be able to answer. Okay, so magnitude of fs is equal to 1. That means the magnitude of this fraction is going to be equal to 1. And the phase of fs is going to be phase of course, the phase of k is 0, since k is a positive number. K is 0. So the phase of fs is the phase of s plus z1, phase of s plus z2, because they will be complex numbers. Remember, s is a complex number. So all the phases of and phase are going to add together for the numerator, and all the phases are going to be subtracted, which are in the denominator. So all the phases of the numerator added together minus all the phases of the denominator subtracted from the phases of the numerator. And that should be equal to 180 degrees plus k times 360. So this is our criteria, of course, for your f of s, which is k times gs. So let's look at this problem first. For the control system shown in figure this, determine the value of k if one of the roots of the characteristic equation is 2 plus 3i. So the characteristic equation is 1 plus k times gs. Gs is 1 over s plus 2. And to calculate the roots of the characteristic equation, of course, we equate it to 0 to calculate roots of them. K over s square plus 2s, or whatever, s plus 2, I'll just leave it right now, equals -1. And we know that the magnitude of this is going to be equal to 1. So from this, we can figure out what is the value of k at any specific value of s. at S is equal to 2 plus J3, A over 2 plus J3, and then 2 plus 2, 4, 4 plus J3. Magnitude of that equals 1. So K will be equal to magnitude of 2 4s are 8, J3, negative 9, negative 9 plus 8 is negative 1. Or you can just do the individually, magnitude individually, doesn't really matter. And 2 times J3 is 6, 4 times 3 is 12, 6 plus 12 is 18. So K will be equal to the magnitude of negative 1 plus J18. So anyone, what will be the magnitude of negative 1 plus J18?
It's 18.027.
18.027. Okay. The value of K, 18.027, should produce one of the roots of the, actually it's not going to be one of the roots, it's going to be complex conjugate because this is a complex root. It's going to produce a complex conjugate root, which will be 2 plus 3i and 2 minus 3i. We can check. Go ahead and open this. Okay, so K is, let's see, 18.027. 027. And your equation is going to be s squared plus 2s plus k equals 0. So roots of s squared plus 2s k equals 0. And it's not producing the correct one. Let's see why not.
Maybe because I rounded up or rounded down.
No, that's, let's see. You're looking at the poles. So negative 1 plus J4 it's not 2 plus 3i. S squared plus 2s plus k. Let's see. What it is now. So let's see. S is equal to 2 plus 3i. And k is equal to absolute value of s times absolute value of s plus 2. Yeah, 8.028, that is correct. Then why it is not giving the correct result then? Let's see. 18.028. KGS over 1 plus KGS. And 1 plus KGS. To find the roots, we equate that to 0. So we have s squared plus 2s plus k divided by ss plus 2. That will be equated to 0. That's going to be gone. Oh, actually, you know what? So give me 1 second. your transfer function is kgs over 1 plus kgs. No, that's the same thing. That is the same thing. That's going to give you k over ss plus 2 over s square plus s 2s. S square plus 2s plus k. So this will give you the poles or roots of the characteristic equation. All right, so if I put, let's do that. S square plus 2s plus k. K is equal to negative s squared minus 2s. And magnitude of k is equal to magnitude of negative s squared minus 2s. So let's calculate that. Should be the correct answer. I'm not sure. It's not giving the correct answer. S is equal to 2 plus 3 pi. And A is equal to negative s square minus 2 times s. 1 minus 18. That's what we got. 1 minus 18. It's equal to the absolute value of the answer. It is 4.2458. That's different than what we got. 18.027.
So you did the absolute value of the answer.
Oh, absolute value of the k. Sorry. Yeah, you're right. The answer is not absolute value of k. No, sorry. Yeah, answer is not S not k. Sorry, yeah, the absolute value of k. K is 1 plus. Oh, k is not this. So hold on. K is equal to negative s square minus 2 times s, and absolute value of k. 18.028. What is not giving us the correct answer? Check if those are the roots. So if I put k is 18.028, let me do it again. Roots. We have s square plus 2s plus k. So s square plus 2s plus k. Oh, interesting. One root is 2 plus 3i, but the root is not. So maybe my thing has an error because I just picked up a number over there. So one root is correct. The both roots should be, of course, complex conjugate on the s plane. So maybe the number that I picked up is not part of the root locus. That could be one of the issues, because not every pole will be part of the root locus. So I think I just picked up a value without realizing that if it is part of the root locus or not. So this might not be part of the root locus. Okay, yeah, that could be the answer. I mean, it is showing that's one of the value, but we are expecting if we have one root as a complex, then of course there's going to be a conjugate for that as well as a complex. So this value may not be part of the root locus. So anyways, this is how we're going to calculate if we have the correct root, that is. But this is the method to calculate that, the value of k. And in this case, of course, as I said, that I might not have taken the correct value, which is part of the root locus, and that's why it's not showing me. It's showing me this value, but it's showing me the other value, which is not the complex conjugate. So that's my mistake. But this is the way to calculate it. And so if you do have root locus, so if you have this equation right here, you have s squared plus 2s plus k. If you change the value of k each time from starting from, let's say, 0 all the way up to a very high value, then your quadratic equation over here, or the characteristic equation over here, it will be different. And for each value of k that you change, it's going to produce two roots. Those roots can be real or complex. If they're complex, it's going to be complex conjugate. If you put together all those roots and then connect them with lines, that's the root locus of this of this characteristic equation. So if I go, let's say if I go, k is equal to 0 to 10, and I do roots. Well, I cannot put k over there. I'll have to use a for loop, basically. I'll just use for k equals 0 to 10. Let's just calculate roots. Roots. You have 1, 2, and k. And 2. So all these answers that you see, starting from when k is equal to 0, your two roots are -2 and 0. When k is equal to 1, your roots are -1 and 1. Then for k is equal to 2, -1 plus j1, -1 minus j1. So anytime you have, of course, complex root, it's going to come in the complex conjugate. K is equal to 3, these. So when you put all these roots, on the S-plane and connect them together. So this is your S-plane. So you have two roots for, let's go and check the roots. -2, 0. So the first root is 0 and -2. Second set of roots are -1 and -1. So you have two roots here. -1, -1. And then likewise you have, -1 plus j minus 1, and so multiple roots. So you start connecting the part of the root locus with certain conditions that we're going to discuss. So your roots, poles can go something like that. Your root locus can go something like that. That this is one of the part. This is one of the part. This is one of the part. And stuff like that. So when you connect these different roots together, the graph that you get is called the root locus graph. But where it is coming from? Again, it is coming from by changing the value of k and evaluating the roots of the characteristic equation every time you change the value of k, and then plotting them on S-plane. And I'm going to show you, for example, this. So you have a 0 over here, and you have 4 poles of your characteristic equation. And then you start changing the value of k. So now this is your root loci, as you can see. So from this pole, it is moving this one. So these are symmetric. And then from this pole, it is going towards this 0. And from this pole, it is going towards infinity. How did I get that? Again, I got it by changing the value of k and then putting the roots on the S-plane and then connecting the specific root loci together. Now, which one I'm going to connect? That's what you have to see. So characteristics of root locus plot. Now, this is basically where we are discussing how to plot it manually, not with the computer, but manually how to plot it. So instead of discussing how to sketch and approximate root locus by hand, which can always be done accurately with computers, let's discuss important characteristics. So these characteristics is basically how you're going to plot it and where the roots are going to be located, but you're not required to do that with hand, as I said. So each section of root locus plot starts at one of the poles of GS and ends at one of the zeros of GS. If number of poles are more than number of zeros, then those sections start at poles and then move towards infinity, where we assume that a zero is located at the infinity. So what does this mean? This is your 1 plus kgs is equal to 0. And we know that GS can be represented as m zeros and in this case n poles. So S plus Z1, S plus Z2, product of that. So you have factors of the polynomial in the numerator that represent m zeros. Those zeros can be real or complex. And likewise, you have factors of the denominator, poles, real or complex. Now, if you look at this, then go to the next slide. You can write that down in terms of S plus Pj plus k times S plus Zi is equal to 0. S plus Pj times 1 plus k times S plus Zi divided by S plus Pj, and this will become 0 when you cross multiply with 0. So you can have S plus Pj, product of S plus Pj, this is a product sign, remember, plus k, S plus Zi is equal to 0. That's what you see here. So observe that at each pole, value of k will be 0. Why? Because at each pole, S plus Pj is going to be 0. This product is going to become 0. When you put, let's say your pole is S plus 3. So you're going to put the pole is at -3. So this factor is going to become 0 when you put S is equal to -3. And you will be left with k times product of all zeros is equal to 0. That means k is equal to 0. So when k is equal to 0, you're going to have each of the pole of this characteristic equation. When k is equal to 0, you're going to have each of the pole of this characteristic equation. And that's how I drew this. All these 4 poles that you see, I don't know what is the characteristic equation for that. This right here, this is the characteristic equation. So you have poles -1, -10, -7 plus 7i, and -7 minus 7i. These are the 4 poles, and 1 0 is at -5. So when k is equal to 0, the values that you're gonna get from the characteristic equation will represent the poles of the characteristic equation. And those poles are these. So for these poles, the value of k is 0. So it's starting from there, because you have to change the value of k from 0 to onward. So it starts at k is equal to 0, and those are the 4 poles of the characteristic equation. In this case, -1, -10, -7 minus 7i, -7 plus 7i. And of course, you have 1 0 at -5, which is right over here, -5. So that's the first thing that you mark down, the poles and zeros when you have k is equal to 0. If your number of poles are greater than the number of zeros, right here, sorry. And as k tends to infinity, as you start increasing the value of k and it hits infinity, roots of the characteristic equation will be heading towards zeros of GS. Why? Because this is your equation. 1 plus kgs is equal to 0. Or, k times this is equal to -1. So when you will put k is equal to infinity, or when k is going to be infinity in this case, let's put this. Is equal to -1. And k will be equal to sum of product of all the poles divided by product of all the zeros, cross multiply, and the magnitude we are taking, so we're gonna do the magnitude of it. So observe that the product of 0 is in the denominator. So anytime you're gonna put s as one of the roots of the denominator is going to become 0, which means as we are moving towards a 0, the value of k is going towards infinity. It's increasing. And as we're going to approach towards 0, when the denominator becomes 0, k is going to hit infinity. Again, limit we are talking about. Of course, at 0, it's not going to exist. The fraction is not going to exist. But when we are going towards 0, k is becoming greater and greater. And when we are very, very close to 0 in terms of limit, then of course k becomes infinity. So that means when, yes.
You said if the product's in the denominator, it always approaches 0. Is that what you said?
No, I'm saying if you put s as one of the zeros in the in this equation. So let's say s plus. So let's say you have two poles. You have s is equal to -5, s is equal to -7, right? So your denominator is going to be s plus 5 and s plus 7. So if you put s equals -5, then one of the factor is going to become 0 in the denominator.
Okay, gotcha.
Right. So k is going to become infinity in the limits. Of course, it's not going to exist at 0, but if you put the limit, then it's going to be infinity. Which means that when k is going towards infinity, basically the value of s is going towards one of its zeros. Right? Make sense? Earlier we said that when k is 0, then we are going towards one of the poles. So if you put the value of a pole, if your poles are, in this equation, let's say, if your poles are, any -3, -2, or whatever the poles are, if we put any value of this over here, let's say s plus 3. So if you put s is equal to -3 as one of the poles, this is going to become 0, and you're going to have k product of all the zeros is equal to 0, which will make k is equal to 0, because of course you do have zeros that exist. So either this will be 0 or this will be 0. So the only thing is, the only 0 quantity is going to be the value of k, the controller gain, that will make the whole product to go down to 0. So it starts, when k is 0, it starts at poles. So at any value of pole of the characteristic equation, the value of k is going to be 0. And at any value of 0 of the characteristic equation, the value of k is going to hit infinity. So it starts, when you're changing the value of k, it starts at 0, it starts at a pole, and it moves towards a 0 as you're increasing the value of k. So if you have more poles than zeros in the equation, for example, here you have 1 0, s plus 5, and you have 4 poles. So you have 3 more poles than zeros. You have only 1 0 and 4 poles. So if you have n poles and m zeros, where n is greater than m, then there will be n minus m zeros located at infinity, and there will be n minus m root-locus branches heading towards infinity. So observe this. So this is the root-locus of this equation. So you have 4 poles, you have one finite zero. Now observe when you start changing the value of k from 0 to a very high value, and of course you cannot put an infinity value. I don't know what value did I choose for k, 1000 or something. I don't remember. But when you start from 0 to infinity and start combining those roots that you have, then the root that started from s is equal to, let's see what this is, s is equal to -1. So the one that started at x is equal to -1, it moves towards this 0 that was at s is equal to -5. So that's one of the root loci, Root-Locus. The root that started at 7 and -7j or something, and 7 and a +7j, they started going towards some of the zeros that will be sitting at infinity if this keeps on increasing. That is, if you keep on increasing the value of k. So this curve is gonna keep on extending. So if you take an asymptote, along this line, then we assume that there's a 0 sitting at infinity, and this curve is going towards that 0. Likewise, same for this. And the pole that is sitting at s is equal to -10, the loci from this pole start heading towards infinity, with the 0 that is sitting along the -infinity. S is equal to -infinity. So this Root-Locus has 4 sections, as you can see. When you start changing the value of k and start accumulating the values of all the roots and start connecting them through a line, then you will get these 4 sections of the Root-Locus. So once again, how did I create this? I have this equation right over here. So this equation is going to be what? S plus 1 times S plus 10. So this is S4 plus 25S cubed plus 262 S square plus 1218 S plus 980 plus K times S plus 5. So your equation is S4 plus 25S cubed plus 262S square plus 1218S plus 980 plus K S plus 5, which is equal to 0. Because you're calculating the roots, so of course you're going to equate it to 0. Denominator is going to hit 0, because when you cross multiply to 0, denominator will become 0. So this polynomial is going to be 0. So you have S4 plus 25S cubed plus 262S squared plus 1218S plus KS. So 1218 plus KS, and then 980 plus 5K plus 980 plus 5K equals 0. So now if you change the value of k each time starting at 0, so at 0, those are the poles of this characteristic equation right here. -1, -10, 7 plus 7i, and -7 plus 7i, and -7 minus 7i. So those are the 4 poles of this characteristic of GS, poles of GS. And when k hit infinity, then you'll have the 0 of GS. So the first step is you go ahead and you plot those things. What are the poles of GS and the zeros of GS? You go ahead and those are your initial points. You plot those points. And then you start changing the value of k. Starting from, let's say, 0.1, 0.2, or 1 to whatever you want, whatever interval. The closer the interval, the closer the roots are going to be, and the line is going to be smooth. So when k is 0.1, you collected some roots. is 0.2, you collected some roots. 0.3 collected some roots. So you will be collecting 4 roots for each one of them. And like we did earlier, for an example, what was that? I think I deleted the for loop that I was running. Oh, no, it's right. Okay. So now you have, when k is equal to 0, your roots are -2 and 0. So your poles are -2 and 0. When k will be 1, your poles are -1 and. So you're going to combine the first 2 and the second 2 together. The first one, first one, first one. So for all the first one, they're going to be combined together. All the second one, they're going to be combined together. If you have, of course, your polynomial is 5th order, 6th order. So you're going to combine all the poles, first poles together, or on the graph, actually, they will be together anyways. Second one, third one, fourth one. And those will be connected with a line. And those will be part of the root loci. You guys following me? This is a S4 equation. So you have 4 roots. Observe, we have 4 paths. So the first one is going to be combined with all the first one will be combined together, all the second one will be combined together, all the third one will be combined together, roots that is. And from those roots, when they will be plotted, these paths will be created. If you have a 5th order, then you may have 5 different root loci for the complete root locus. You have a 6th order polynomial, you have 6 different paths. So that's how your root locus is going to be generated. What is the purpose? Actually, before we go to the purpose, let's see what are the characteristic I was discussing with you. So the root locus on the so you will have m root m zeros sitting at infinity if n is greater than m, and those zeros will be n minus m. Like in this case, you have 3 zeros sitting at infinity because you have 4 finite poles and 1 finite 0. So you have a 1 0 sitting at here infinity, 1 0 sitting along this line at infinity, and 1 0 sitting at this line along infinity. Because of course it starts at pole and heads towards infinity. That's why we say that starting at pole heads towards 0. That's why we say that those zeros are sitting at infinity. Because as you keep changing the value of k, as it start increasing, this line will just keep on extending. This line keep on extending. This line keep on extending. This won't extend because it starts at this pole and ends at this 0. Root locus on the real axis in the S-plane always lie to the left of an odd number of poles and zeros. And what does that mean? Again, you're not drawing it with your hand. That simply means that if you have a part of root locus on the real axis, then anytime on the right-hand side, you have odd number of zeros and poles total, then that section of your x-axis will be part of the root locus. So for example, in this case, as you can see, you have only 1 pole over here. So this part is part of the root locus on the real axis. Since on the right-hand side of this, you have only a single or odd number pole. Now observe, this is not part of the root locus because on the right-hand side, you have 1 0 and 1 pole, which means you have an even number of poles and zeros. Here, you have 1, 2, 3, 4, 5, odd number of poles and zeros. That's why this whole section on the x-axis is part of the root locus. So once again, this, if you're drawing with freehand, of course, with a computer, you don't really need to do that. But this is one of the things that you have to be careful about, as what are the sections of the real axis that are part of the root locus. And again, as I said, you don't have to do it with the freehand. You're doing using computers anyways. Observe there are 4 poles. Okay, observe the section of root locus in accordance with that. The root locus is always symmetric about y-axis, since any value of k that will produce a complex pole, there will always be conjugate for that, as we discussed. So as you can see, these sections, which are combination of all complex poles, they are symmetric to each other, because every complex pole is going to exist as complex conjugate. If there are more poles than 0, some sections of the root locus will be heading towards infinity, as we discussed. Center and phase of the asymptotes with which root loci will move towards infinity may be calculated as center of asymptotes are calculated as poles of PS, sum of poles of PS minus sum of poles of sum of zeros of PS divided by n minus m, and the angle with which those root loci are going to head towards infinity can be calculated as the angle or the asymptotes 2k plus 1 over n minus 1 times 180 degrees. So again, you're not doing it. I'm not asking you to do that, but this is one of the rules. For example, for this, we have the center of asymptotes. We have 4 poles, -1, -10, -7 plus 7i, -7 minus 7i, minus 1, 0, which is -5, divided by n minus m, which is 3. So I have -6.667. And then the angle of asymptotes with respect to x-axis is given by 2 times k plus 1 times 180 divided by n minus m. So 60 degrees, 180 degrees, 300 degrees, so on and so forth. So go back over here again. So they are heading towards infinity, as you can see. This is 180 degrees. This is 30 degrees. What were the values? Let me go check. 60 degrees, 180 degrees, 300 degrees. So that's 60 degrees. And that's 300 degrees, or -60 degrees. And then one is 180 degrees. So these are the asymptotes, along with the section of the root loci are going to grow that are going towards infinity. And the asymptote is this. So when you extend this, I'm doing a poor job, but this point is -6.667, which is the center of the asymptote, which is calculated over here. If root locus crosses imaginary axis, those complex conjugate values of s can be calculated using Root-Hurwitz's method, as we did the third case of the Root-Hurwitz. We can use that to calculate the imaginary values. However, when you plot this and you extend this, you can easily read those values either from the graph or from your program, that these roots are crossing the imaginary axis, which is at 0. And you can calculate the corresponding value of the k when it crosses the imaginary axis. That is when the system becomes marginally stable. You can calculate the value of k from what? From this equation right here, what we calculated. We used right over there. 1 plus kgs is equal to 0. So if you know the value of s from your root locus, that it will cross the y-axis, then you can read that value from either the plot or from your program and calculate the corresponding value of k that will make the system marginally stable. Actually, from the program, you can also just find the value of k instead of calculating, because you will have vectors with the value of k and the corresponding roots. The point where roots leave the real axis and enters in the complex plane, yielding complex conjugate roots, is called breakaway point, and it can easily be determined graphically. So in this case, you don't really, really. Okay. So what is the breakaway point? If you have a root locus such that, and most of the time it happens when you have two poles, and then it starts moving towards this pole, start moving towards here, and at some point, since root locus starts at pole and at 0, so it cannot go towards each other. At some point, it breaks away from the real axis. One goes here and the other goes here, and there will be 0 sitting at infinity. So this condition is very common. So in that case, this point is going to call the breakaway point. That is when the root loci are going to leave the real axis and enter into the complex plane. So that's the breakaway point. So the angle with which a section of root locus departs from a complex pole is called angle of departure. And likewise, the section of root loci arrives at a complex pole is called angle of arrival. It's important to calculate if root locus sketch is drawn with hand, but it's not so important if you're drawing with a program. So what does that mean again? That means if you have a pole, if you have a 0 sitting over here somewhere, or if you have, let's say you have a pole over here or 0 over here, then from one of the poles, your curve is coming towards a 0. Then this angle with which it is coming with respect to x-axis, this is called angle of arrival. Angle of arrival. And from the pole, if it is going towards a 0, like in this case, then once again, the angle that you have over here with respect to x-axis, that's called angle of departure. That's what it means, angle of arrival, because arrive towards 0 and depart from a pole. So those are angle of arrival and angle of departure. So for this case, angle of departure is 180 degrees. It is going towards this 0. Angle of departure is 180 degrees again. It is going towards 0, which is sitting at infinity. In this case, you can calculate it. Again, we are not calculating it, but it can be calculated easily. And likewise, in this case, angle of arrival can be calculated easily as well. But those are called angle of arrival and angle of departure. Once again, arrival is departure is from pole of the characteristic equation when k is 0, and arrival is at zeros, 1, 0, 2, 0, whatever the finite zeros, and rest of the zeros are going to be sitting at infinity. All right, let's see, what do we have? PID is going to be next topic, next week.
Professor,
Yes.
I wrote the MATLAB code with the example we were doing, but it has the asymptote lines if you wanted to show that.
I'm sorry? You're using Root-Locus right here?
Yeah, I was doing the example, the one that we have with the plot, but then
here, are you using Root-Locus? I forgot.
Page 10.
Okay, so yeah, MATLAB has Root-Locus function. You're using Root-Locus, right?
Yes.
Yeah. So if you use Root-Locus function, if R EKG load control. So if you use our locus function, define a system, like we did the transfer function system and stuff, you define a system and use our locus, is going to plot the our locus values. Our locus system increment minimum value of k and maximum value of k. So you can use that to calculate R locus. I'm going to give you a project in which basically you are going to be calculating, you're going to be changing the value of k and calculating the roots and then putting them together. So the way like I did over here, putting them together to create a root locus. But you can always use R locus to create the root locus of any. So let's create it real quick. So your transfer function is equal to transfer function. What do we have? S plus 5. Let's put it here. So 1, 5. And I have S4, 1, 25, 262, 12, 18, 12, 18, 980. Oops, point start. That's my transfer function. And when we are using the root locus, and since I don't use it very frequently, I usually forget the format. Let's see what is the format. You have R locus. Oh, we can just do R locus system and see if it works. R locus. Otherwise, you can define your own value of k and stuff. R locus of sys. So something like that. So these are the asymptotes along with when these line goes and they're gonna meet. This is the center of the asymptote as we discussed. These are the angle of the asymptotes. And these are the sections as I showed you. So you have 1, 0, and then you have 4 poles right over here. And the angle of departure can be calculated. We're not calculating here, but this is the angle of departure right over here. Likewise, angle of departure from here, which will be the negative of this angle. And the angle of departure of this is 180 degrees. Angle of departure is 180 degrees with this as well. But yeah, this is the root locus of that transfer function or characteristic equation. Now you can, as you saw in the help, you can define your own value of k, maximum, minimum, all those values. You can define all those yourself. You can see when it is, so this value is, let's see, what is this value? When it intersects 0. Negative 12.78, so negative j 12.78 and positive j 12.78 approximately. Yeah. MATLAB it's easy to do. Octave it's not. So whatever the value when it intersects the 0 axis, that's where the roots, that's where the system is going to become marginally stable. Negative 12.9 or something, j 12.9 positive 12.9. Well, this is the root locus with the R locus function that is in the MATLAB. But remember, the basic concept is what? That you are calculating the roots of that quadratic, roots of that characteristic equation by changing the value of k. And you are basically putting together all of those roots, all of the first roots, all of the second roots, all of the third roots, all of the fourth root. In this case, there are 4. In this case, there are 4. So why you have to use symbolic and everything, can't you?
I did that so I didn't have to have just the coefficients, but also if you use the Root-Locus X, it will become interactive, almost like MATLAB.
Okay.
Or if you click on it, it'll give you the value of K.
Oh, okay. Yeah, MATLAB does give you the value of K, right? Yeah. So anyways, yeah, you can do that. And again, if you want to look at the help is there, and you can do that. So let's see what is left today, and then I don't think I don't know if there's a homework that I will assign you from this. I'll have to check. But there's one example that we want to do. Determine the value of K for which the root locus shown in figure 7.3 will cross imaginary axis. Also calculate the roots on the imaginary axis. So we already did that. And as Andre said, let me open chat. So you are doing sim-to-poly S+5 sim-to-poly. So is that the what you call, Andre, is the help, MATLAB help that you checked?
I had to go in their website on Octave, and I found it
Their
there.
website. Okay. All right. You can also do from the documentation. I think it should be there. Function index. I don't know if it's going to be the same or different.
I don't think they have it there since it's a
They don't?
package that loads.
Yeah, it doesn't look like that. It has over here. GHI. Yeah, it doesn't look like it has it. Okay, so online, you checked it online, right?
Yeah, on their website, I just
the
searched for their
Okay.
the function.
All right. Well, everyone can do that, of course. So I'm not going to spend time on that. But again, plotting is not difficult. As I said, plotting is very simple. You have the built-in function, and of course, the concept is that you're changing the value of K, collecting all those roots. So I guess when I created the program, I created vectors for all the roots. All first root, there's a vector. All second root, there's a vector. All third roots, there's a vector, and all fourth root, there's a vector. And then I just went ahead and plot all those vectors on the S-plane, on this, basically, on the same plane. I plotted all those vectors. So yes, hold on and hold off, basically, when you're plotting a graph. And that's how you plotted all those things. What was the problem that we were discussing? Let's see. Determine the value of K for which the root locus shown in figure 7.3 will cross the imaginary axis. Also calculate the roots on the imaginary axis. So, where is the equation that we have? Oh, right here. So we have this equation: S4 plus 25SQ plus 262S square, 1218S plus 980 plus KS plus 5. So let's write this down. S4 plus 25SQ. S is S4 plus 25SQ plus 262S square plus 1218 plus KS plus 262S square plus 1218 plus KS and 980 plus 5K. Plus 980 plus 5. So that's your characteristic equation equal to 0. When we create the root harvests, one 262, 980 plus 5, 25, and 1218 plus K. B naught, B1, and C naught, and D. So when we calculate B naught, that is going to be 125, 262, 128. Okay, so that's going to be negative 1 over 25, 1218 plus K minus 262 times 25. Calculate that real quick. It's going to be in terms of K. So I have 262 times 25, and this is 25, so that's going to be 262, and minus 1218 times K. This is plus K. 1218 plus K. 1218 plus K over 25. And that's going to be negative 1218 plus K over 25. So we can simplify it real quick. B naught is 262 minus 1218 over 25. 262 minus 1218 over 25. That's 213.28. So 213.28 minus K over 25. So I'm just going to leave it like that. And then B1 is going to be negative 1 over 25. 1 over 25, and then this is 0, so 1 times 0, and then negative 25 times 980 plus 5K. So this is going to be 980 plus 5K. B1 is 980 plus 5K. And then C naught is going to be negative 1 over B naught. 25 times B1, 1218 times B naught. So 25 times B1 minus 1218 plus K times B naught. So that's going to give us 1218 plus K. B naught and B naught will be cancelled out. Minus 25 B1 over B. I'm doing it correct. So in order for the poles to be on the y-axis, the C naught is going to be 0, so that we can calculate the pole from this equation. That will give us the complex conjugate poles. So if C naught is 0, what we are going to get? C naught is equal to 0 implies we have 1218 plus K is equal to 25 B1 over B naught, or K is equal to 25 B1 over B naught minus 1218. B1 is this, B naught is that. So we'll have to do some crazy simplification basically. And if I want to do it right now, since the class is about to end, well, let's try. Insert, new slide. Bye. So 1218 plus K, 25 B1 over B naught. One two one eight plus K. What is that? 1218 plus K is equal to 25 B1 over B naught equals 25, and B1 is 980 plus 5K. $980 plus 5K, and B naught is 262 over negative 1218 plus k 213.28 minus k over 25. 213.28 minus k over 25. So as you can see, it's a little crazy. It's going to be a square equation most likely. Let's see. So 25 times this. All right, so let's see what I'm doing at 25. 1281. I'm going to get the correct answer or not, but let's try it. So you have 25 times that, and that's going to become 25 square. Let's see. 25, let's say A is equal to 25 times 213.28. That's going to be 5332. 1218 plus A equals 25 squared. This 25 is going to go on top. And that's going to be 980 plus 5K divided by 5332 minus K. And then we multiply these two together. 1218 plus K times 5332 minus K is equal to 25 squared 980 plus 5. So I'm not going to solve the whole thing, but it's going to give you an equation of K squared plus some K plus a constant value. So it's a quadratic equation that's going to give you. From that quadratic equation, you're going to get two roots. And generally, those two roots are one value is positive, one value is negative in general. Let me see if I can do it. How much time do I have? I don't have much time. That's the only problem. I have 1218 negative K plus 5332 K. And then I have this, so negative 25 squared times 5K. That's my K's. And then I have a negative K squared. And then 1218 times 5532. 332. And then I have 25 squared times 980. So minus 25 squared times 980 is equal to 0. And I'm going to multiply the whole thing by a negative sign. So I'm going to get K squared. And let's see. I don't think it's going to take long. So let me just do it quickly. So I have 5332. 5332 minus 25. So that's 5 cubed, basically 5 cubed. 25 times 5. And then I have another K somewhere. Let's see. Do I have another K? Yeah, negative 1218. Negative 1218. So that's my K. That's going to be 3989. And with a negative value, negative 3989. And then I have the constant, which is 1218 times 5332. 1218 times 5332 minus 25 square times 985, which would be 5881876, and that's going to be a negative sign. So minus 5881876. 881876. So that's going to be 0. Let's see what are the roots of this quadratic equation. So you'll see roots 1, comma, negative 3989, negative 3989, comma, negative 5881876. Okay, so you have two values, 5134.5 and negative 1145.5 for value of k. Which value is the correct value? Who's going to tell me? That is if our process is correct. But let's say our process is correct. Which value is the correct value of k out of these two? That we are trying to figure out what value of k is going to produce poles on the y-axis. So it will make the system marginally stable. As you could see, there are two poles on the y-axis. These two poles right here at 0, 1, and 2. There are two poles on the y-axis. So we're trying to figure out what is the corresponding value. Now, which value is reasonable?
The negative value?
No, negative value is not reasonable because k value is positive always. It starts at 0 and ends at infinity. So 5134.5. A is equal to 513. And I don't know if the value is correct or not. I may have made a mistake or something. I don't know. But if everything is correct, then 5134.5 is a probable value since the other value of k is negative. So when you have the value of k that you think that if you did not make any mistake is going to produce roots on the y-axis, then you can write down your equation from this s square, which will be b naught s square plus b1 is equal to 0. Calculate the value of b naught for the value of k. Let's see if we can do that quickly. 213. So let's say k is equal to answer 1. So b naught is 213.28 minus k over 25. And then b1 is 980 plus 5 times. No. Oh, it's lowercase k, it's uppercase k. Lowercase k is different. So 2.66. So I have 7.8980 s square plus 2.6653 exponent 4. It doesn't look very good because our roots are 12 or something. That's not going to produce a root of 12. Maybe I made a mistake or something. Somewhere I made a mistake because the value of y is 12 point something, but this is not going to produce 12. Yeah, there's no way this is going to produce 12. Roots b naught, comma, b1. Oh, no. Roots b naught, s square plus 0, s square plus 0 s plus b. Yeah, that's producing 58. That's not the correct value. So I have made some mistakes somewhere. That's producing 58. So that's showing me that the value of s is somewhere not here, but somewhere down here. even further down, 15. But here, the value of S from the graph, which is easy to see, is 12.897. Andre, from your graph, what is the value of K that is producing the root on the complex plane?
You mean on the y-axis?
On the y-axis, yeah.
I got 2,900.
Okay, so 2,900 something, not 5,134. So somewhere in my process, I made a mistake, and my value is coming out to be a value that is different than what we have. But again, goes back to how you're going to calculate it. Of course, you can always do it from the graph, especially if you have MATLAB, then it gives you a very clear thing. But even in Octave, you can do that. But if you have to calculate that value, then this is how you go about it. You write the equation down, and then you do the Root-Hurwitz criteria. And from that Root-Hurwitz criteria, this is going to be 0. Find the value of K when this is going to be 0. And that value of K is going to be substituted for B0 and B1, because when this will be 0, that means this equation is going to give you complex conjugate roots on the y-axis. And so you can see it's quite messy. So it's just you make a mistake somewhere, and then it's just going to be hard to calculate when you make a mistake somewhere. And that's why I don't really do it. I use graph most of the time. I ask you to use graph as well. But the basic thing, you can do it. You can read the value of S, then use the use the criteria. 1 plus Fs is equal to 0, and then calculate the value of K from there and all those things. So that is your root locus. This is how you draw the root locus, as the collection of all the roots that you are getting from the characteristic equation when you're changing the value of the controller gain. And the polynomial of the characteristic equation will tell you how many root loci are going to be there. That is, how many sections of the root locus are going to be there. If it is s to the power 4, then you have 4 sections, as you can see, because you have 4 roots. So every time you change the value of K, you're going to get 4 roots. So you're just going to combine the first root together, second root, third root, fourth root together, and connect them together on the S-plane to get 4 root loci. The first step is, of course, to put the poles of the characteristic equation when K is equal to 0, and the zeros of the characteristic equation. And then all the poles will be combined together, as you can see over here. So that is the root locus. And again, I'm not going to ask you to draw with the hand as I used to. I realized that that's not fun for students, and it doesn't serve any purpose anyways. So you're not going to ask to draw it, but you should know how to create it using MATLAB and how to read values. And if I ask you to get the value of a specific root, or if there's a specific root, like the problem that we did right over here somewhere. If it's a specific root that is given from the root locus, then how to calculate the value of K for that specific root, even if you don't have the root locus or whatever. So these things are important, because again, when you're designing a control system and designing the gain of the control system, you want to know, again, remember, what purpose does the root serve? The root, or the pole, basically, it serves the purpose of how fast your transient response is going to decay. What will be your sinusoidal frequency? So all those things that you're designing for a control system, that comes from poles. So if you're designing for a specific gain of the control system that is producing a specific set of roots, that will determine the response of your system. The speed of the system, transient decay of the system, sustained value, and all those things. And that's why it is important to figure out, for any value of the controller gain, what is going to be different roots for that. Or if you know the roots, then what will be the corresponding value of the gain of the control. So that is your root locus.